Hi, this is Dr. Lesher, and this is a video to introduce the topic of gases, and it's about mostly pressure in this video. So think about what a gas is. If you think about a basketball or any type of ball that you've ever inflated, when you attach a pump to a basketball, you're putting tons of molecules of air into that basketball. And what's keeping that basketball bouncy and the way it should be is the motion of all those molecules against the interior walls of the basketball. So that pressure is high inside the basketball compared to the typical atmospheric pressure. So a nice quote I like from the textbook is that pressure is caused by these individual collisions, but the overall property is really the collective result of lots and lots of these molecules. So we can characterize gases with a number of measurements: pressure, volume, temperature, and the number of moles of gas present. And these are abbreviated with the symbols that are listed here. But the bigger question is, why bother? Why do we talk about gases in chemistry? And there's two main reasons that I would point to. First, one is that the atmosphere, what we breathe, is all gases. As an environmental chemist, that's really a critical thing that we study. And then secondly, lots of chemical reactions produce gases, and they're interesting. So that's why we study them. So let's think about the atmosphere for a bit. If you're like anything like me, if you have a straw and a drink, you've done the little trick depicted here, and that's to put your finger over the top of the straw and lift your drink out of the cup. A barometer works in the same way. In both cases, the air pressure, the atmospheric pressure, is holding liquid inside a tube. In the case of the straw, it's just kind of fun to move your drink around and spill it on the table. In the case of a barometer, it's actually used to measure atmospheric pressure. So here's what a barometer actually looks like. You could construct a pretty simple barometer if you have a whole bunch of mercury, which is kind of difficult to come by nowadays, and a glass tube. And the way you would make the barometer is to fill the tube completely with the mercury, put your finger over it, turn it over, and then let go of your finger once it's sitting underneath the surface of a little dish of mercury. And what happens is that weight of mercury will be pulled down, creating a vacuum in the top of the glass tube. It's not going to fall all the way out of the glass tube though, because there's atmospheric pressure acting on the little pool of mercury in the dish, and that pressure is counterbalancing the pressure caused by the weight of the mercury. So the barometer at typical atmospheric pressure supports a mercury column that's 760 millimeters tall. But of course that varies a little bit with the weather. And yeah, that atmospheric pressure is counterbalancing the pressure caused by that column of mercury, which is a function of the density of mercury, gravitational force, and height. So atmospheric pressure can vary day to day. I just pulled these weather conditions up, so October 12th, and you see our temperature, you see our humidity, our wind. What you see here is the atmospheric pressure, and it's expressed in inches. Now, what does that really mean? Well, that's actually inches of mercury. So we're in the United States, we typically use inches. But if you convert that to millimeters, that's 768.4 millimeters. So today, atmospheric pressure is relatively high. That typically happens when there's good weather, and it's been nice lately. But the pressure is dropping a little bit. So another similar instrument for measuring pressures of gases are called manometers. And these aren't used terribly often anymore, but they're really illustrative of sort of the interactions between pressures of gas samples and atmospheric pressures. So a manometer is a U-shaped glass tube that's open on this end, on the right of your screen, and it's attached to a gas sample on the left side. And there's mercury in the U of the glass tube. Now you can kind of imagine if you just had an open U and you poured some mercury into it, you would have that mercury kind of filling both sides of the U, and the levels would be even if they were both open to the atmosphere. Instead of having both ends of the U open to the atmosphere, one end is connected to a gas sample. And so this is a way that we can measure the pressure of the gas sample. by comparing how much it's pushing on that mercury compared to the atmosphere. So what we see in this picture is that the gas sample is pushing less on the mercury than the atmosphere is. And so that means that the pressure of the gas sample is less than the pressure of the atmosphere, as indicated by the fact that the atmospheric pressure is pushing down more on the mercury and causing it to rise up the tube towards the gas sample. So how would it be different if there was a highly pressurized gas sample here? Well then, a high pressure, greater than atmospheric pressure, will be pushing this mercury down the other way and making it rise up higher in the on the right side of the U. We can actually quantify pressures of gas samples in this way. So here's a blow up of the part of the manometer right here where the blue arrow is. And so we can see that the pressure of the gas is less than the pressure of the atmosphere because that mercury is higher on the side where the gas sample is attached, so that the atmospheric pressure is pushing harder on the mercury than the gas sample is. We can calculate that actual pressure. We can see there's a difference between these two levels of 9 times 2, or 18 millimeters of mercury. So if we subtract 18 millimeters of mercury from the 752, that tells us that our pressure of the gas is equal to 734 millimeters of mercury. So what units do we use for pressure? We've just been talking about millimeters of mercury, which is a very literal unit. We're actually measuring with a ruler the millimeters of mercury. But there's many other units that we use for gases. There's really, for pressures of gases, there's really too many. We have ATM, which we use a lot in chemistry, millimeters of mercury, torr, Pascal, kilopascal, and bar, and they're all used in chemistry. There's even more if you think about ones that are used in other fields. You might be familiar with PSI or others. Now, the relationship between these units is right here. 1 atmosphere is 760 millimeters of mercury. The torr is the same thing as a millimeter of mercury, just a little, easier to say. So 760 millimeters of mercury, or torr, is equal to 101,300 pascals, or 101.3 kilopascals, or 1.013 bars. So that's kind of a mouthful, and we often need to be converting among units of pressure. So just like any other conversion, we need a conversion factor where the top and the bottom are equal. And given this handy list of the equalities of all these pressure units, that's not a hard task. Let's say we're asked to convert 750 millimeters of mercury to ATM. We need a conversion factor that relates those two units. And we just have to make sure that the top and bottom are equal to each other. So on the bottom, I want 760 millimeters of mercury to cancel out, or I want the unit millimeter of mercury to cancel out. So I have an equality of 760 millimeters of mercury to 1 ATM, and that gives me slightly less than 1 ATM. 32 kilopascals to millimeters of mercury. I start with my 32 kilopascals, and then I insert values that are equal to one another for kilopascals on the bottom, 101.3, 760 millimeters of mercury on the top, and that gives me 240 millimeters of mercury. Last example, 3.5 ATM to bar. The ATM and the bar are almost equal to each other, they're very close, but 1 ATM is equal to 1.013 bar. Significant figures are important in these unit conversions. 1 ATM is kind of the reference value, that's exact, so you don't have to worry about there only being one significant figure there. But all these other ones are limited by the digits according to the rules of significant figures. So that's it for today. We'll continue talking about this in class.